Hello, everyone. Thanks a lot for attending today. And I'll be speaking, as Jacques already announced, on our most recent paper, which is on ensemble meta-labeling. And I guess most of you are familiar already. This is a series of papers on meta-labeling, which started by Jacques with a paper on theory and framework, and then one more paper on meta-labeling architectures, and one more on position sizing. And I think 2 weeks ago, Michael already talked about the position sizing one. So this paper builds on top of all of them. And I'm going to talk to you about that today. So what we did in that paper is that we investigated different ensemble methods for meta-labeling with applications in finance. And our aim was to present a framework to facilitate the selection of ensemble learning models for this purpose. And we did it by conducting 2 experiments. So the first one was on information advantage, and the second one on modeling for false positives. And by that experiments, we tried to discover whether ensembles are better at extracting and detecting regimes, and whether they could increase the model efficiency. And our findings are that ensembles are especially beneficial if the underlying data generation consists of multiple regimes and is nonlinear. And this framework is intended to start as a starting point for further research to conduct, because as you will see, our findings are very case dependent. So if you have a given primary strategy or primary model, then whatever ensemble architecture is going to be the best depends heavily on what your underlying model is. So I'm going to talk you through the 4 sections of the paper, which is first I start with the theoretical framework. So what is ensemble learning? What is model selection, and a bit of background on meta-labeling. Then next, I'll focus on the methodology, where I go through the research aims, questions, and hypotheses. Then which data generation process we used, what our primary and secondary models were. Then I talk specifically about the meta-labeling ensembles, and finally about position sizing and the strategy creation. And then in the results, I will speak about the results of the 2 experiments. So the first experiment on information advantage, and the second on modeling for false positives. And this is going to be followed by a brief discussion and conclusion. Oops. So if there are 3 points I would like to highlight today, or that you should remember from this paper, is that the first point on ensembles general superiority. So the proposed framework demonstrates how several individual models can be combined to obtain a better generalization performance. Then the second point is about regimes and model robustness. So we demonstrate how ensembles improve the detection and extraction of regimes, leading to a higher model robustness. And the third point is on model efficiency and increased meta premium. So we show how ensembles increase model efficiency by decreasing the rate of false positives, which leads to an increase in meta premium. And for context, the meta premium in meta-labeling describes the gain of the secondary model. So but it's going to be, we'll see that later in the experiments. So there are basically 2 main reasons to apply ensemble learning. The first one is performance, the second one is robustness. And if we speak about performance, is that compared to a single contributor model, an ensemble can predict events more accurately and perform better overall. So the basic idea is that by merging numerous models, these allow the mistakes of one model to be compensated for by others. And that's boosting the overall ensemble prediction performance over that of any single model. And with regards to robustness, an ensemble narrows the prediction and model performance distribution. So that means like an improved robustness and reliability in the model's average performance, which is another a very important benefit, but not as well known as probably performance. So yeah, like those are two reasons to apply ensemble learning, but you may occasionally prefer one or the other. So like that is something to keep in mind when you choose your ensembles, because later on we will see that like some of our ensembles are better in performance, whereas others are more robust. Okay, so like then model selection. So like in model selection, you basically like we differentiate between like models of the same type, but with different, like a different configuration. Like think of different hyperparameters, like different kernels in a support vector machine, or models of different kinds, such as like logistic regression, support vector machine, or k-nearest neighbors. And like the point of model selection is that when you create a classification or regression predictive model, you like it's impossible to predict beforehand which model is going to solve the problem best. Therefore, it's necessary to fit a variety of models and to evaluate their performance. And therefore, model selection is the process by which we statistically evaluate and compare potential models before selecting the best one. So in contrast, model assessment involves evaluating a model after it has been selected to convey how well it's anticipated to perform in general. So both evaluate, like model assessment and model selection, but at different steps. Then wait. So from next is meta-labeling, and the goal of ensemble learning is to enable more accurate predictions that would be possible with any of an individual algorithm. So in a way, it's a wisdom of the crowds method that compiles data from several models into a set of remarkable accurate findings. And in that way, you could think of meta-labeling as an ensemble as well. However, there's a very important difference, and that is that whereas you have in meta-labeling also like different models, a primary and a secondary model, they have completely different purposes. Whereas in ensemble learning, you have the same purposes. And so first, we develop a primary model that provides good recall, and even if the accuracy is not particularly great. And then the idea of the second model is that you compensate for the low performance by applying meta-labeling to the positives predicted from the primary model. So as we will see later on, meta-labeling is especially beneficial when you try to improve F1 results. And the key is to train a secondary machine learning model to utilize the primary model. And this leads to an improvement in performance parameters as accuracy, precision, and F1 score, where you trade off some recall. So like when we speak of meta-labeling, then it's like in general in like a finance context or applications for finance, but like any setting where you have like a trade-off between recall for F1 would be a possible application of meta-labeling.
One thing before you move on there, Dennis, let's just go back one. So if we go back to the previous slide.
This one?
Oh. No, use your arrow keys and then you can go back. There we go. This one. No, one on where we're looking at the architecture.
This one?
There we go. Yeah, that's the one. I don't know if anyone has any questions here. I mean, this is a good place to ask. This diagram is actually from the very first paper on the meta-labeling theory and framework. And this very specifically speaks to, how we, what is a way in which we can think of meta-labeling. And so I don't know if there are any questions anyone would like to ask about the architecture. Maybe there's something you don't understand about the framework. Now's a good time to raise the question, and I can help answer any questions. It doesn't look like there are any questions. Of course, if you do have a question, you can just leave it in the chat and then I'll answer it there in the background as Dennis is lecturing. Cool. Over to you, Dennis.
Yeah, like I forgot to mention it in the beginning. Obviously, if you have any questions or if anything is unclear, then please feel free to raise your hand or interrupt me, and I'll try to provide more context or help with that. Okay. So like now we move on to the methodology and to our research aims, questions, and hypotheses. So as I mentioned before, the goal of the study was to develop an ensemble learning model selection framework for meta-labeling. And it's like our hypothesis is very straightforward, that an ensemble classifier would outperform a single baseline classifier. And one of the reasons, or like potential benefits of ensemble learning, is its ability to handle concept drift from non-stationary distributions. And in this context, there are like two characteristics in the method from ensemble learning, and that is like, how do you create diversity within an ensemble? And the second is like, which method do you choose to combine them? And moreover, like one of the goals beforehand is that your base learners should have like a high sensitivity and efficient learning ability. And as you'll see later on in our experiments, we compared shallow models, so like logistic regression, for example, and also deep models like a neural network. And another important point to consider is the correlation strength, because again, ensemble learning, you try to create low correlated ensembles to increase the ensemble diversity. So then if you move on to the synthetic data generation, for each of the experiments, we applied a quadruple autoregressive process that was used to generate 10,000 sequential daily returns. And by quadruple autoregressive process, I mean that it consisted of 4 separate AR3 processes, because there were 4 different regimes. First, a positive negative algebraic sign swap, and second, low and high volatility. So because we had a long only strategy, we filtered out those predictions of the primary model that would predict a positive change in direction. And then afterwards, we applied a 60-40 train test split without shuffling. And if you look at the data generation process, so RT are the returns. So the daily returns, and then RT-1 and RT-2 are lagged by 1 or 2 days. And the numbers before the returns, those are the model coefficients, and those here, we have 80, which is the drift component. So that is a noise series with a mean of 0 and the variance of 0.00212 for the low volatility regime and 0.00423 for the high volatility regime. And for those volatility numbers, we used a random sample of IBM's returns.
I think just one thing to highlight here is, this is the same kind of setup that we used in the, in the first paper. So there's actually a 4th paper that we're also working on. But it's just this kind of idea that, if we use an autoregressive process to generate the time series, then we know very clearly, what are the features which are driving, which features are going to be informative. We don't have to sit here and play around with an autoencoder, to compress the features or principal component analysis or apply any moving averages over the data. We don't have to do any of that. We know exactly what's generating the data. And that just gives us a lot of control in terms of, us measuring the experiment, us figuring out which part is due to the information advantage, which part is due to modeling for false positives. And so, when we were thinking about the ensemble learning, we thought that, let us introduce more types of regimes in the data, because we expect that with ensemble learning, it will be able to better account for those regimes. And like Dennis mentioned, Dennis, if you just repeat, you were saying that ensemble learning allows you to handle model drift.
Yeah. So yeah, so like our aim was to investigate the superiority of an ensemble over a single model, and therefore we introduced these different drift and volatility regimes, and that was achieved by altering the variance of AT for the volatility regimes, and how we did that by introducing a uniform random number between 0 and 1, and a threshold of 0.8. So if this threshold was passed, then we used the high volatility regime, and if not, it was in the low volatility regime. And this process was repeated every 30 observations. So
yeah, just adding on to that, so the core idea is that we've got some kind of at the end of 30 observations being generated, we have kind of like a random number that's generated, and if that number is greater than a certain threshold, then we pick that the next 30 observations are generated using one of those 4 distributions. And so we're introducing, that was kind of inheriting this idea that regimes are kind of slow moving, that they persist for long periods of time, and we tied that up from other literature we had read. And so we kind of introduced the idea of regime shifts in the data by doing that.
Yeah, and if you look at it, we used linear processes, but obviously what we thought is that for example, if you exponentiate the returns, you would introduce a nonlinear component, and we would suggest to do that because I think that would further show the superiority of ensembles compared to a single model. However, you have to keep in mind that if you use a nonlinear data generation process, you also have to use a nonlinear base model, whereas we, as we will later see, use a logistic regression as a baseline model to keep the setting comparable to Jacques' first paper. Okay, then I move on to the primary model. So for the primary model was based on the German power autocorrelation strategy that was introduced by Narro and Kamanos. So it's basically trend following, and it generates an end of day buy signal with a restriction of long only. So if the price difference between yesterday's close and today's close is positive, we go long at today's close, otherwise we exit the position. And in the formula, you can see the delta RT is the difference in returns between RT and RT minus 1. And epsilon T is the side of the position. So if we, a buy or a sell.
And let me just jump in here. Just the one thing to say. So sorry, not a trend following strategy, but a momentum strategy, because you can have trends in the data even with a random walk. You will observe that you get these types of trends that emerge. It is just completely random. So because it's an autocorrelation strategy, it actually falls more in the definition of a momentum strategy. So slightly different to trend following, but very closely related. So sorry, Dennis, that was just the one thing.
Yeah, true. Thanks.
And this trading strategy actually comes from a book which I use quite frequently when I was a trader at an energy company. I just want to see if I can find it. Here we go. So for those of you looking to learn more about the strategy, so this textbook, Systematic Trading in Energy Markets, one of the chapter talks about that they advocate that you start every kind of trading strategy process with a autocorrelation model as a benchmark strategy. So if you're interested in that kind of thing, this textbook is what you're looking for.
Okay, great. Then for the secondary model, So like the idea in meta-labeling for the secondary model is to ascertain whether the prime model site prediction was accurate and whether a position should be taken. And as I already started saying before, is that since this is like a binary classification setting, we use the logistic regression as our baseline because it offers good explainability and requires few tuning parameters. And if we look at the features that the secondary model uses, those are RT, RT-1, and RT-2. And in addition, we also have the regime detection indicator that tells us which of the 4 processes was used, because those are flagged accordingly. And because we intended to simulate the lag effect of a statistic that uses window size, this regime indicator was also lagged by 5 observations. Then we standardized the data by eliminating the mean and scaling each feature to unit variance. And the target variable of the secondary model is the meta label, so whether the prediction result or the prediction of the primary model resulted in a gain or in a loss. So epsilon t is the meta label, and no, yeah. So that shows us the site forecast from the primary model. And we didn't apply any regularization or hyperparameter tuning to make it easier to interpret the results. Okay, then we come to the core part of the methodology, and this is the meta-labeling ensembles. So in addition to the logistic regression, we built ensembles for our secondary model. So if we go back to the very first, wait, to this slide. So this is where we actually applied the ensembles at for the secondary model. And we built 3 ensembles. So and when selecting your ensembles, you have to consider a bias variance trade-off. So low bias and high variance modes include decision trees, k-nearest neighbors, and SVMs, also support vector machines. And examples for high bias and low variance models are linear or logistic regression and linear discriminant analysis. And then in ensemble learning, you can either select your model statically or dynamically. So static selection is the more popular one, or the well-known one, which is averaging all members of the ensemble pool. And static selection criteria are classification and diversity measures such as accuracy or correlation. Whereas in dynamic selection, you look at the feature space. So you select the best combination of classifiers for each data sample. Because the idea is that beforehand, you can't predict which of the combiner will produce the best results. And the 3 different ensemble frameworks that we used are first a sequential ensemble with a light gradient boosting machine. Second, a homogeneous dynamic ensemble selection with a random forest. And third, a heterogeneous dynamic ensemble with a classifier pool. So when I talked before about same models and different models, or models of different kind and models of same kind. So homogeneous means models of same kind. Like in a random forest, you have decision trees, whereas heterogeneous means models of different kinds. So for our classifier pool, we use the logistic regression, a decision tree classifier, a support vector classifier, a naive Bayes, a multilayer perceptron, and exactly, and a multilayer perceptron. Because our idea was to make in light of low bias and high variance models to cover all of them. Okay, then I move to the first ensemble, that is the right as the boosting ensemble. So this one, like light GPM, has a few advantages that makes it quite popular. It improved gradient boosting by a form of autonomous feature selection and concentrating on boosting cases with greater gradients. So this increase results in a significant increase in training speed, enhanced prediction performance, and that's one of the reasons it's especially good for dealing with tabular data, for regression and classification predictive modeling tasks, which why amongst extreme gradient boosting, it is one of the most popular ensemble techniques. And if we look into the flowchart, so X1 to Xn represent the feature data sets, and M21 to M21N, those are the weight increase boosted decision tree classifiers. So this figure is actually from a previous paper by Michal, where he introduced the different meta-labeling architectures, and we intended to apply some, or like implement some of them and compare them. So the next ensemble was the dynamic ensemble with a random forest. So for our dynamic ensembles, we relied on a technique that is called NORA, which is K nearest neighbor oracle. And that basically locates the nearest K neighbors for each data point in a validation set, which determines which classifiers correctly classifies those neighbors and uses the neighbors as an ensemble. So, and we used the random forest because it's one of the most successful ensemble methods, which is an extension of bagging, with the main distinction that it includes randomly selected features. So, and like a random forest, basically, like when you build a component of the decision tree, at each stage of the split selection, the random forest first selects a subset of the features before performing a standard split selection procedure with a chosen feature subset. So if we look again at the flowchart, we see that B1 to Bn represent the sample data sets for the feature X, and again, M21 to M2N are the meta-labeling decision trees classifiers. So then we come to our final ensemble, which is the dynamic pool. So for our pool of classifiers, we aim to cover different areas of the feature space. And as an example, support vector machines is a maximum margin method. Those produce distinctive distortion in their predictions. So they tend to shift the probabilities away from 0 and 1, producing like a sigmoidal shape. And if you use naive Bayes, for example, it's the opposite. They push the predictions towards 1 and 2. So it's like the probability is very split towards the edges. And then you have techniques like back trees or neural nets, for which you have very well calibrated probabilities. So that's why like we used logistic regression for high bias, low variance model, the support vector classifier for high variance, low bias model, and naive Bayes to its unique distribution of outputs, as well as a neural network, in our case, a multi-layer perceptron, and decision trees, which are well calibrated to maximize the data exploitation. And if you look again at the flowchart, we see that M2 to M1, those are our meta-labeling classifiers, so the 5 I mentioned. And we, again, as in the previous dynamic ensemble, we used Nora for the dynamic ensemble selection. Okay, so then I finally come to the last part of the methodology, which is the position sizing and strategy creation. So we applied an all or nothing algorithm. So when a favorable outcome was predicted, 100% of the portfolio was invested. Otherwise, the algorithm exited or held the position size of 0. So if we look at the formula, Ft is the size of the position at time t, and epsilon hat t is the secondary model's prediction of a positive outcome. So because we so the strategy basically works in that way that we only took a long position when the prime model advised going long, and the secondary model confirmed this prediction. And then yeah, like we from this approach, we this yielded out the size of the position. Okay, then we come. Whoops. Should be this one. Cool. Then we come to the results and the 2 experiments. So if we remember before, like our 2 research questions, we have experiment 1 for information advantage, and experiment 2 for the modeling of false positives. And in experiment 1, the primary model only used delta RT to predict the site. However, this disregards the fact that RT-1 and RT-2 are also of informative value, which will be used in experiment 2. And then we produce a more precise forecast by fitting the secondary model that would take this data into account. And the meta premium is the difference in the trading strategy between the secondary and the primary model. So for the first experiment, this table shows us the changes in strategy metrics, and we can observe that the ensemble classifiers had a positive premium across all metrics. However, this wasn't.
Sorry.
Yeah.
Sorry, Dennis, I just want to make sure everyone understands what the information advantage is. So the information advantage is very specifically when we were trying to figure out what is actually like the outperformance that comes. So the real question when you first start thinking about this is, how can I show what the value add is of applying meta-labeling? So you apply it, you see that it does better, but then you have to think about how can we do attribution? So how can we attribute outperformance due to specific features or way that models are extracting information in the data? And so the information advantage, what we saw was, so we first gave the simple example in our very first paper where if we use a the primary model actually only uses the previous day's lag return, right? So the direction of yesterday's lag, if it was a positive day, we'll go long. If it's a negative day, we'll go short. And so it only uses 1 day's worth of information in order to make a forecast. Then when we apply meta-labeling, you'll see that we use all the available information, which actually includes lags 2 and 3 as well. And because you've got lags 2s and 3, you then kind of have, you have like more information available to you. So when we were then we're thinking, okay, information advantage, what does this mean, right? So the information advantage very specifically just means, all right, if we use the same features as like the primary model, but we're fitting it with kind of a machine learning model that use that information in a better way, and we saw an outperformance, that would then be called the information advantage. So without adding any additional information relative to, for example, regimes, so we're not including data yet for, that would be indicative of a regime change. We're just adding, the the last 3 days lags, and now we're fitting a model to it, and we're seeing that, oh yeah, this is a really good, like very obvious example of showing that it would have this kind of effect on the data. So we're seeing an information advantage that if you're just passing through the features that were used by the primary model, that the secondary model is able to extract that information in a better way. And usually because, using an ML model rather than some kind of like rules-based heuristic that suboptimally extracts information out of the data. And so if we see a positive information advantage, that just means that by adding a ML model on top of it, it was able to extract information from the data in a better way. And then the modeling for false positives is now, okay, now we're adding features which would be indicative of a false positive. Do we see an additional outperformance? And that's what Dennis is going to show you. So this first part is just relating to, do we see an outperformance when we add meta-labeling, and it's exploiting the information in that data better than the heuristic primary model.
Okay, thanks a lot, Jax, for the clarification. So what we can observe is that for the ensemble classifiers, we have higher expected returns and lower expected standard deviations, and this results in increased Sharpe ratio. And therefore, we conclude that meta-labeling is effective when it can use the data more effectively than the primary model. However, since we use a quadruple autoregressive linear process to generate our data, the logistic regression didn't perform as well as with the single autoregression that Jacques used in his paper. So, and the explanation is that different models use data in different way. So increasing model diversity may improve performance when the underlying data consists of more regimes and is nonlinear. And this is going to, and we can see this as well if you look at the changes in classification metrics. So those like these box plots again illustrate difference in classification metrics between the secondary and the primary models, and a net increase in performance is indicated by a positive change, as the case for precision, whereas a decrease is a negative change, as it is the case for recall. So as we'll see in the next slide, the F1 score improves significantly for all models, which indicates a more effective classifier that can eliminate false positives by sacrificing some recall for greater precision. That's why we have negative values for recall, because we trade off recall for the other measures. And
sorry, just a quick one, Dennis. So
yeah.
I quickly went to the first paper just to get the strict definition of what we're saying information advantages. So I'm just going to read it here to everyone. So experiment 1 focuses on improving the information advantage and seeks to answer the question, should the features used in the primary model also be used in the secondary model? This is an important question because if you read blog posts at this point in time, you would have seen that there are professionals that advocate not to use features that were used in the primary model in the secondary model. And I wanted to show by way of experiment that that's not true. You should use, like, the features that were present in the primary should also be present in the secondary. And so I note here that the primary model only made use of the delta of the last return when predicting the psi. This is a simple strategy that fails to consider that the lag 2 and lag 3 are also informative. By fitting a secondary model which includes this data, a more accurate forecast can be made. And then, these exhibits show the statistics of that. And so that's what that's just the strict definition of information advantage.
Okay, thanks a lot, Jacques. And if we look specifically on our ensembles, then we will observe that the light gradient boosting machine and the dynamic ensemble selection with a random forest appear to be the most robust, because like if you look at the box plots, those seem to have the those seem to have the least variation. It's especially demonstrated if you look at the recall.
The one thing I want to, oh, sorry, Dennis.
No, please go ahead.
The one thing I wanted to highlight here is, again, we're seeing that precision recall trade-off that Lopez de Prado was talking about, that we would, be filtering out bad trades, hence you see a drop in recall. But by filtering out bad trades, we make, trades that are more, we get more of those trades correct. And so we see precision go up. And so you're seeing a recall for precision trade-off.
Thanks for that. So if we look at these box plots, obviously the question arises, why is there like a large variation for the dynamically selected pool? And I'll come to that point later in the discussion. So now we move on to the second experiment, which is on false positive modeling and how to reduce false positives. And here again, those values are the meter premiums. So IP is for the information advantage and FP is for the false positives. So what we can see is that FP outperforms IP in every situation. So that was what Jacques highlighted, is that if you incorporate more features, they actually help increasing the performance. And thus we can conclude that modeling for false positives enhances the value of the meter premium. And similar to the first experiment, we observed that the ensembles outperform the prime model in terms of the Sharpe ratio and mean returns. However, if we look at the Sharpe IP, the Sharpe ratio for the information advantage of the logistic regression, we will see that this has a negative value. So that emphasizes that occasionally modeling solely for information advantage is results in worse returns than solely the primary model. And the reason for this is that changing regimes make it challenging for the logistic regression to find a good fit. Whereas our ensembles adjust better to the regime shifts and contribute to positive value changes. So in addition, we can see that the delta Sharpe ratio FP is always positive for the ensembles, indicating that even like losing strategies become profitable once modeling for false positives included. So that like also applies for the logistic regression. Then if we move on to the change in classification metrics, the blue box plots are for the information advantage, the orange ones for the false positives. So like once more, these box plots highlights that all metrics improve solely compared to the using the information advantage. And we have a very similar behavior to experiment 1, where again, we trade off some recall for a gain in precision, accuracy, and FM score. And similar to the first experiment, we see that our ensembles, so the last 3 models, consistently outperform the logistic regression. That is also true for the next slide. And again, yeah.
Sorry, Dennis, if we can just go back one slide.
Yeah.
I just want to emphasize the fact what we're seeing here is that meta-labeling is quite effective of handling, the problem of non-stationarity in financial time series data, that certain trading strategies we've observed, perform well during certain market regimes, and when those regimes change, they perform less well. And so, we love the research that comes, so Man AHL has a blog post, and they often post, I think Campbell Harvey did a blog post about in which regimes, what trading strategies perform best in inflationary regimes. This came out about 1.5 years ago when, COVID had just kind of finished. we were entering this phase of like, okay, a period of high inflation, and the question was, what kind of trading strategies, we're going to outperform the market during that type of inflationary regime. And they advocated for trend following and momentum-based strategies. But that's the problem in trading, right? Is that you'll trade a strategy and then it'll start performing badly because you go into a different market regime. And so what we're showing is that meta labeling is an effective mechanic, to control for those changing regimes. That the model goes and it determines, okay, you've got to trade a primary trading strategy. You're saying you want to go a long position, but given the market state, do I think we should indeed take a long position? And so it just is really effective for filtering out when not to trade. And so we're seeing that behavior kind of consistent throughout these experiments.
Okay, thanks a lot, Jack. So I move on to the discussion now and to start wrapping up things. So just to recall, our aim was to develop a framework to facilitate the selection of models for meta-labeling with ensemble learning. And we conducted 2 experiments on information advantage and modeling for false positives to discover whether ensembles were better at extracting and detecting regimes and whether they increased model efficiency. And as I mentioned before, the 2 reasons to apply ensemble learning is improved performance and robustness. And we were able to establish the validity of the trade-off between recall and precision that Jack observed already, as well as the fact that using ensembles in meta-labeling further enhances both classification and strategy metrics. And amongst our tested ensembles, the light gradient boosting machine and the dynamically selected random forest delivered the most robust performance. So in general, we can conclude that the results show that ensembles outperform single base learners, especially when the underlying data consists of many regimes. Thus, we can support our hypothesis that ensembles should be selected as a model for meta-labeling. So obviously the question arises why, where does better performance of ensembles comes from? And that is because different models use data in different ways, which leads to increased diversity and optimized data exploitation. And this benefit, as we were able to observe, is especially dominant when the underlying data consists of more regimes and is nonlinear. And then again, as I already mentioned, we observed like a larger variation in the classification metric scores for the dynamically selected heterogeneous pool. And that might be because those individual base learners have different distributions of outputs, which actually is one of the intentions why we aim to include them and combine them. But our chosen approach, the k-nearest neighbor oracle, is trying to unite them, and that, as we saw, isn't working that well always. So one of these issues is that the generation techniques for dynamic ensembles are based on bagging or heterogeneous classifiers, and they were designed for static combination methods. So in other words, they generate basic classifiers using a global method, because like in static selection, you have a global rather than a local perspective, whereas in dynamic selection, you want to ensure the participation of local experts, which isn't guaranteed. So we would therefore suggest, or like our explanation is that our selected dynamic selection approach might be unable to identify competent local classifiers, and therefore like an investigation of fusion strategies to take this local information into account would be able, could be a solution to narrow down the variation that we observed in our heterogeneous pool. And then obviously one of the limitations of our analysis is that we used synthetic data that and did some assumptions which are not satisfied in real world data. And also like we couldn't really tell, or we can't conclude like in general, which is the best ensemble. So it's really case dependent on what primary model you have and what underlying strategy you apply. But like we hope to, like our aim was to provide a guidance on how to answer this question on a case dependent basis. And then I finally come to the conclusion, where I like to recall the two research questions that guided us through this paper. So first of all, we can confirm our hypothesis that an ensemble outperforms single baseline classifiers. And this is like the basic idea is a theorem called the Condorcet's jury theorem, that a majority decision is more likely to be correct. And in experiment 1, we demonstrated how ensembles increase the information advantage through improved detection and extraction of regimes. Subsequently, in the second experiment, we showed how ensemble improved the model efficiency by reducing false positives. And concerning the ensemble architectures, we would conclude, or we could observe that the light gradient boosting machine and the homogeneous dynamically selected ensembles with a random forest classifier offer the most promising results because of their great performance and superior robustness. So we would recommend starting with either of these two architectures. Although, like when we looked at the box plots, we saw that the heterogeneous pool provided some potential. However, because of its large variance in the classification metrics, there must be it's necessary to investigate a better fusion strategy. So, finally, to conclude, if you assume that you have already an underlying strategy and a primary model that generates your trading signals, the best ensemble is still dependent on what your underlying strategy and what primary model you have. So yeah, with this final words, I'd like to conclude my presentation, and I'm happy to take your questions.
Perfect. Thanks, Dennis. I'll stop the recording in a second. The only other thing I think is really worthwhile mentioning is that if you read the original paper, you'll see that Dennis provides a 5-step framework for applying ensemble learning to meta-labeling, and in a couple of, so it's in the appendix of the paper, and in there he usually gives like a description of how to think of that in the context of meta-labeling. If you apply something, how getting model diversity is definitely a benefit that we're looking for. And I think it's quite a few words, like 2,000 words or something, just on the model selection framework over there. So yeah, that's it. I'm gonna stop the recording here, and then I'll open to the floor if anyone has any questions.